Welcome to Module 11, Supervised Machine Learning Classification. In this module, we present neural network classification, and in the end, we apply the neural network classification methodology by demonstrating the compressor shaft vibration classification. As we already had before, in the very beginning, we present the main concept of artificial intelligence applied for maintenance 4.0. So here in this glossary, you have the concept of artificial intelligence, machine learning, unsupervised machine learning, supervised machine learning classification, supervised machine learning regression. This model will focus on supervised machine learning classification. Therefore, based on a different methodology or tools that's part of artificial intelligence, we are discussing machine learning, and to be more specific, supervised machine learning classification. The general concept of machine learning is to use a dataset, split the dataset in training and test data, use the training dataset to training a model, and then we apply the test data to test this model. That's the so-called verification. If the error that we've got from the test data is acceptable, we can use a new data set similar to what we have the previous one and use in the model. And if the error is acceptable, we validate this model. Then we can constantly use similar data to this model. In supervised machine learning classification, we have the same structure. Our models in classification aims to classify our data in different features that is already predefined. So that means in our dataset, we already have one specific classification for our data. Then we're going to split this dataset in training and test. We choose one model. In this case that we are presenting here is the neural network model. Then we train this database in this model. Then we use the test data, that's 30% of total data set, to verify how good are the model. Then if we got a good result of this data, we use a new data set similar to the first one to validate this data. We have now different type of supervised machine learning classification. The first one that we'll present is the neural network classification. After this model, we go one by one, present different type of methodologies for you to have a clear idea how are the difference between different supervised machine learning classification methods. In the end of the classification method, we'll come out with a confusion matrix, and then you can get a result similar with that shows the percentage of data that is true classified, true positive classified in this main diagonal matrix. And then, of course, we will be able to see different set of data, such as the validation and the test data, the training data, and all data together. So let's go to the neural network concept again. As we saw in a model, a self-organized map that we use a neural network. Neural network is a model that mimics human neurons that pass relevant information for each other. So our neural network are organized in input layer, hidden layers, and output layers. Between the layers, we have the wave that enable to get the functions that we have in the hidden layer and go to the output based on the output functions that we use. We are going to see now that we have not only this feedforward network, but we have also the backpropagation network. And the backpropagation network aims to minimize the error and update in the wave. So the main elements that we have is the input vectors, the waves that we have in between two layers. They have the function x, that's the wave sum of inputs, and we have the activation function here that will define in the end the output of each layer, and that will define the classification in the end. So just to clarify, we have one of these classification function is the sigmoid function. So here is the formula. In the end, depends on the value that we apply here, we get some value close to 1 and 0, and those are these two classes that we can have. Actually, that is the simplest example that we can have, two-class classification, and then based on the value that we've got the function, if it's closer than 1, we have one class, let's say high degradation, and if we have values close to lower, we've got values of lower degradation. That's all depends the value that's come and out of its function. And this value, of course, go through the neural network and depends on the value that will come out in this last function here to input the variable z. So let's see an example to see how does it works. Let's consider this very simple neural network. So based on this neural network, I need to first calculate the fx function. So the fx here function is, I need to calculate the bias, that is 1 multiplied for this wave plus this vector value x1 multiplied for wave 2 plus x2 multiplied for wave 3 and then I have the fx. Then based on this fx, I will input this fx in the fz function, and then I will got my classification. So basically what I have when I look on my sigmoid function is this z value. So this is equal to fx. So when I apply fx here, I will get values close to 1 and 0, and those are my two classes. So 0 I can define as, for example, no critical, and 1 high, very critical, or 0 as moderate, and 1 as high in terms of alarm of degradation. So let's take a look on an example to see how we are. So consider that we have the wave 1, 2 equal to 2, 2, 2 equal to -4, and 3, 2 equal to -4. We need to find first, as first step of a neural network, is to find fx. So fx will be the bias multiplied for the wave 2, this 1 multiplied for 2, that will be fx will be equal to 2 plus x1 multiplied for -4, so 2 multiplied for -4, x1, and x2 multiplied for this wave that's -4, that is we have in the end fx equal to 2 minus -4 x1 minus 4 x2 is what we have here as fx, and the fx is equal to z as we represented here. So we have the same for each one of the fz function, the activate function, that we want to classify different data. So now we have 4 data we want to classify in two classes, 0 and 1. And then by applying the first case is the point 1, 2 is a point 0 and 0, 0. So x1 and x2 is 0. So if we replace x1 and x2 here, we've got this equation that is 0.1 is close to 1. So we define as class 0. So in the second case, we have the point 0 and 1. If we apply here 0 and 1, we've got this equation here. We have -2 here. Then we've got 0.9 that's close to 1, the class 1. It's classified as 1 is class 1. And the third point is 1 and 0. If we replace x1 and x2 here by 1 and 0, we've got -2. That's again 0.9 is classified, is close to 1, is class 1. And then the last one, 1 and 1, we have by applying in this equation here the fx, we've got -6 if we put -1 and -1, we have -6, and we got 0.99. That's close to 1 class 1. So we have 3 points that's classified as class 1 and 1 point classified as class 0. So graphically, what we have is the first point is class 0, and the other point is different class. So we can split the region in the graph here and classify these 4 points in 2 classes. And that's the principle that we have in the neural network. So the second part of neural network is what we call backforward process. And the backforward process, the main objective is to classify the error. That is defined based on this equation here. So we have the k is the number of outputs. We have yk label class of the input vector. So label class predicted here, OK, and then we apply just the simple equation. We can get the final result. So by applying this equation, we can get the values of 0 and 1. So 0 and 1, and then the label class predicted here is 0.1 and 0.9. And then, of course, that was the class that we had, that we really had a class 0 and 1, and what was predicted 0.1, 0.9. Then the error here is 0.01. This error is used to update the waves. And how we updated the waves? So initially, I want to see the contribution of each wave for the total error. So I apply this partial derivative in this equation. Then, of course, I have the one important factor here is the learning rate. That's why I apply my equation and previous application of neural network. I already demonstrated that this value is between 0 and 1. If we want to have a fast learning process, we put values closer to 1. If we have a delayed, delayed learning process, we put values close to 0. So that's the learning rates. And then, of course, the partial derivation is represented for this equation here, and we have 3 parameters. That is the one that we use in the final equation to update the waves. So just consider one example that we had. We have the error, the predicted class, and the real class and the predicted class here. So the first part of this derivation. So here we use the predicted value. So we got 0.9, and here we got the wave, so -2. Of course, I can use directly the value of this equation. So I have these sigma values for 1, 2, 3, and 4. So by using this directly formula, so this formula just use the predicted value and the current value here. So for each one of the points, I have 4 points that I use. I can use one sigma value here, and then by having the sigma value, I use the sigma value in this equation here. That's the equation that I updated the points. So the first point here is the values of the updated points by applying this value here and using the learning function. So I have the updating wave, and then of course I have the updating wave. I will go through the process, the neural network again, to update the whole process. So now let's take a look on an example, a more complex. If I want to classify the compressor shaft vibration in 2 levels, let's say medium and high. So for medium values, I have this class 0. Of high values, I have class 1. And then I will use this data initially to remember that I will get 30% of the values of this data set here to train my model, and the 30% of this data set, I will verify if my model have a acceptable error. It's not overfitting. Overfitting means that the model is too much adjusted to the training data, and that means if I have a new data, probably I will not get a good result. So that's why I perform my verification test, and then of course if it's good, I can use a new model. In the end, of course, I will get this confusion matrix. We already saw what's the meaning of the confusion matrix. That's demonstrate that we have here in this, for this case, we have for a training, we have 4 confusion matrix. The first one is consider only the training data. So here the training data, we have 100% of the true positive values, so proper classification, as well as for the test data and for the training data, for all data, consider all data. And we have here also validated data. This validation actually is 50% of the data sets that they've got to make this validation. Okay, and here we have an ROC that shows the data fits properly, the correlation between the true positive rates and false positive rates is very good. So that is the format that we've got. So let's take a look how does it works when we apply, give an example by apply a MATLAB software. So again, we use the MATLAB to give an example. We go inside the neural network for classification, and then based on the classification method, it's very similar to what we had before. We will see that we got our data classified. So let's take a look on what type of result we've got. So here we are open our MATLAB template. We're going directly to the app and we choose our neural network for classification. So here we are. Now we can see that we have a different neural network characteristic in here. We have a leader here, output layer, and output. That's the configuration different that we had when we apply the self-organizing map, but the concept in the end is quite the same. So we move forward. We need now to input 2 matrix information. One is the main matrix, the main file that have the values that I want to perform the classification. So I go to my classification files in the genetic algorithm and get this function. So when I imports the function, they will come out here. So and I will be able to see the 30 lines. There are 30 different compressors with different vibration compressors shafts vibration values with different in column 1 and column 2 different compressors degradation shafts degradation progression signatures. So now what I'm going to do is to validate this matrix. So here we are. Remember that I put here matrix rows. That's bare configuration. And now what I've got to do is the classification for these values of compressor shaft vibration and degradation progression signatures. So now I have one specific matrix here that's called class. So you can see I just open and import the class, and then this data will come out here as this matrix. Remember that the matrix has the same number of lines, 30 lines. There I have 30 compressors shafts values of vibration and degradation progression signatures, And for each one of these line, for each one of these compressor shaft vibration, I define already one classification. So 0 means, let's say, medium value, medium criticality, or medium value for degradation, and 1 means high value. So here now I have my classification matrix, and then I just finish here. Then I'm ready now to move forward to the next step. And the next step, what's going to happen is the data will shows up and how and ask me basically is predefined for this software, how much percent of the data I want to use in my training data, and how much percent I use to testing and validate. Okay, so since I have 30 data samples, I have 20 used to in my network classification methods, and I use 5 samples for testing, five samples for test, and 5 samples for validation. Then I move forward, and the next step is about the hidden layers. So here I can put whatever layers I want to include here. I can put 5 hidden layers, I can put 10 hidden layers, and more hidden layers, theoretically more precise will be the model. So that's basically what I'm going to do here, is to use 5 hidden layers. Then next step now is to go to the training template. So now I move to the training template, and I can train and get the results of my neural network. So I don't need to come out with a neural network configuration. I don't need to define the configuration as defined by input vectors. So I just define how many layers is based on my input matrix. Is already defined how much input vectors do I have. In my case, I have 30. And then now I will going to train the neural network. And then, of course, you see here below that's the training is taking place. Now takes the time. And then, of course, I get these results for my neural network. And here you can see that I have the results here. So very interesting. I have here the cross entropy error measure. So the error is very low here, and we can see I can plot the confusion matrix. So my confusion matrix now will plot the confusion matrix for training data, for validating data, for test data, and for whole data. So that's what I've got here. So I have my training confusion matrix as we saw before. We have 20 data, so we have 100% of accuracy. So because all of them are true, let's say is true classified, and that's what for training data we have the same. For the 5 testing data are true positives, and we have for validation the 5 true positives, and then for the whole data we have all all the data were true positive, of course. So this result is automatically, so that means all the classification, the metrics were properly applied. And then of course I got my ROC graph, and based on my ROC I can see that for the training data, for the test data, for validation, all of them have very perfect fit, and that is the format when these are true positive and false positive gets in this format close to this region of the graph. Another important graphic is the performance one, and the performance one will show the cross entropy versus the epochs. Epochs is a complete number of the training. Then you can see that we have a 33 complete training. Then we get the minimum value that is not more advantage to go further to reprocess the data for inputs and calculate the activate functions to minimize the error. So we can see here how the error will reducing after we perform this 33 training process. And that's very important information. This graph here, they sometimes they will show that's the optimal number of training, that I don't need to go for too many trainings to have to minimize the error of my network, a neural network. After performing the training, what I want to do is to validate this neural network by using new data sets. So I can go to the next steps, and here on the right side of the screen you can see optionally perform additional tests. So now what I'm going to do is to use the same neural network, but I use a new data set, a new let's say data from different compressor shafts vibration. Then I want to see how this neural network that I already have classify the degradation in medium and high level. So I just open the new data here in my file. So here we are. So I get a new data classification. So I can see that I have only 20 compressors with different values of RMS vibration in the first column and different values of degradation progression signature. And then, of course, I need, as similar as I've done in the previous model, I need to get also the classification for each one of such compressor shaft vibration. So what I need to do is come out here and get the proper data, proper file, that is a class 2. And after that, I will validate. So here we can see the column of zeros, that's a medium criticality and one high criticality, high degradation. That's class that I have two classes, classified 0 and 1, as explained before. And now I will finish them, and now I test my network. So by testing network, they already give me a very low value of error, and then I can check the confusion matrix. And when I check the confusion matrix, I can see that I have two true false positives here, classifier in this matrix. That's fine. That are the values that I have two wrong classification. So that is, you can see, it's very simple to classify the neural network, different metrics, and then of course I can apply this methodology to classify as well the new variables from the new compressor shafts based on the same model. So and that's based on the verification, the validation that we've got. So the advantage of a neural network is flexible method that can produce both clustering, classification, and regression. We already saw clustering and classification. We finished. This model is about classification by using neural network. And in the next, the second day, we see the neural network apply for regression. We can produce results even with misinformation. That's one of the interesting information that we have in the neural network. The final results based on acceptable error consider the initial inputs. We saw that this model, they have the real inputs, and they compare always the real inputs to the predicted one, and then they updated the weight and go to further classification to minimize the error. There are some drawbacks of the neural network. There's no rule to build a neural network, so it is not real clear what's the difference we can get if we have more, if we have, for example, 5 or 10 hidden layers. And for example, there's no rule for that, so we need sometimes to test, and by using that, of course, we get experience. is a black box solution that's not clear. Explain how to get in the final result. Of course, we saw the feed forward step, how does it works, and the back forward step. But when we apply, you saw when we apply the software, we do not get these results. And that is why called black box, and requires a high process power and software to run the solution. And of course, for a very simple example that takes time, if the example that I demonstrated here, we had only uh, 3 input layers, 1 hidden layer, less puts. That require quite uh, effort to do that. Imagine if you have 30 input with 5 hidden layers. You need to calculate everything to classify, as well as forward, back, updated away, and forward, feed forwards again to predict and to have more accurate prediction. So we need to have a powerful software. The example that I'm giving here in the training is simple with 30 inputs data, but we can have much more. And as much as data we have, better is to use a software solution or algorithm such as R, Python, or MATLAB, and then applying that. But that's a request a high power of software solution. So the neural network regression is in the chapter of my book. There is one specific item that explains all what we discussed here in this training. So if you have the book, you see everything in details. Thanks for your attention. If you have some questions, just send to me. Now let's move to the next model.